If you are interested in working with geospatial data at scale, leveraging it in modern data engineering workflows, and using the most up to date cloud native geospatial formats, then you are in the right place. In this tutorial, we will be going through Apache Sedona, a distributed computing framework that allows you to work with geospatial data at large volumes with both vector and raster data. This tutorial will be going through how to work with Apache Sedona, getting set up on your local machine, going through the complete set of functionality in a detailed tutorial, and then at the end, moving our workflow to the cloud by leveraging Wherobots, a cloud platform that supports Apache Sedona. Now, you can go through this complete course and you can actually get access to the notebook, code, data, and everything you need to run this over on my website. Over there, you can find the download links, a copy of this video, and if you choose to do so, you can sign up and go through a short certification program to get a certificate for completing this tutorial. Now, before we jump in, I want to talk a little bit about what Apache Sedona is, talk a little bit about distributed computing for geospatial data, and understand where Sedona fits in with the framework of other geospatial processing frameworks. Now, as I mentioned, Apache Sedona is an open source framework that allows you to work with geospatial data across a number of different distributed computing platforms. The most common of which is Spark or Apache Spark, that allows you to run distributed processes and process data at large volumes. So that begs the question, what is distributed computing and how does it relate to geospatial data? Well, distributed computing is not a new concept. It is something that's been around for a long time, that's sort of anchored in a number of different technologies, but really started to come to fruition with Apache Spark. Prior to that, there were different tools like Hadoop and other systems that allowed you to do distributed computing, but were cumbersome and difficult to set up. Apache Spark really accelerated this process and allowed you to do that with an open source framework, either on your local computer or more commonly in a server or a cloud system. The major advantage here is that when you set up a Spark cluster, it allows you to run a number of different processes on it and process that data without having to spin up additional resources. Effectively, when you want to run a distributed computing process, that means that your data or your process cannot fit on the memory of a single machine. Now, what that means in practice is, imagine you have a data set that you're working with. Let's say you're using it in QGIS or GeoPandas, Python, or some other system, and your memory on your computer crashes. This means that either the data can't fit on your machine or the process that you're running too much memory, so it cannot run on your single machine. Now, under the hood, what Apache Spark or other distributed systems like data warehouses and others do is it takes that process and splits it up across multiple machines. Imagine instead of running it on a single machine, you're running it on four different machines, and then at the end, it assembles that process back into the result that you want. This is an oversimplified explanation of this, but effectively, that's what's taking place. Distributed computing takes that process, splits it across multiple machines, runs it in parallel, so that one process that might take 4 minutes now, imagine it takes 1 minute across four different machines and then reassembles it at the end. Now, the things that it requires to actually do that are a few different steps. First is data partitioning. It needs to be able to split up the data appropriately and spread it across those multiple compute nodes or different systems to process that data in parallel. That will allow you to run those different operations in a parallel processing framework. Instead of one, splits it into four for the specific example, and then reassembles it at the end. This effectively allows you to optimize the memory storage, and for spatial data, you can use a number of different techniques to actually manage this data and partition it appropriately so it spreads in an even way. And then at the end, it brings those results back together and summarizes the result based on the question that you asked. Now, when you compare Apache Sedona with other frameworks, there's a few things to be aware of. I'll start with a few common frameworks that are used to process or work with larger volumes of spatial data so that you can kind of understand how they fit in and compare to Apache Sedona. GeoPandas is probably one of the most popular. I have a tutorial of that if you want to check that out. But the biggest advantage is that it's a Pythonic simple API that allows you to run a number of different spatial operations on files that are stored locally or on cloud storage. The disadvantage of that, even though the library itself is increasingly becoming more optimized, is that it can run only on a single node, that being your computer or a cloud service. If you need to scale that, you need to add more memory or more computing power to that node. PostGIS is probably one of the most advanced spatial SQL systems for processing data. It has the largest number of functions, and with a number of different extensions like PGRAS is one of the most advanced systems for managing spatial data in a database system. It has the largest number of spatial functions for raster and vector data, and with different extensions like PG routing, you can add and extend functionality to do more with that system. Again, PostGIS is constrained to a single node, meaning that it is running on that one single compute instance. If you need more memory or more processing power, you have to add that to that system. In addition, many tables in PostGIS live within memory. You cannot store that on a separate external volume like cloud storage, so for example, AWS S3, Google Cloud Storage, Azure Blob Storage, or others. This means that as your data volume grows, you are going to pay for the memory of that compute instance that you're up and running. And if you need it running 24 hours a day, you'll be paying for it for that entire time. On top of that, you need some database administration overhead. But overall, it is the best database transactional system for updating, inserting records. Another common workflow is DuckDB plus GeoParquet or other spatial file types. DuckDB is super fast for in-memory processing. You can process quite a bit of data with that, running it on a single node. It's a very simple setup, it's easy to install and use, and you can get pretty far with it running spatial SQL operations, and you get generally a performance boost over other systems. DuckDB is still evolving and they're adding additional functions over time, but for a quick operation and running that in a single operation, it's quite usable and scalable. Although the downside is it doesn't have the operations to allow multiple users to connect to it unless you leverage a cloud system like MotherDuck. And additionally, there are some data volume limitations with DuckDB as you start to reach larger data volumes. Apache Sedona, out of all of these, is the only one that is fully distributed. It can spread across multiple workers, leverage a backend system like Apache Spark or others, and you can certainly process larger amounts of data with that. You can run it locally, like we will run today, to show you how you can increase your data processing volumes on your computer. And then, as you need to, you can shift that into a cloud system. That said, the setup is a little bit more complex than something like a GeoPandas or a DuckDB, but we'll be walking through that today to show you exactly how to get up and running. And there is the dependency on Apache Spark or another distributed backend that you have to run. So you do need to be aware that you have to run that. And if you do need to move that in the cloud, of course, there are cloud computing costs that come along with that. Now, Apache Spark is the engine that powers Apache Sedona. Sedona is a functional library that provides functions to run distributed computing on top of Apache Spark. As I mentioned, you can run it on different systems. There is Sedona Snow for running in Snowflake, and then you can also run that on Apache Flink as well. In addition, there are other engines that are being developed to leverage Sedona on. So be aware, and as those are updated, I'll put a link in this video so you can get access to those as well, and probably a tutorial video too. Spark leverages two concepts known as RDDs, or resilient distributed datasets, and dataframes as data structures in there. Dataframes will sound familiar if you're used to the Pandas or GeoPandas ecosystem, and they are effectively similar with a little bit of a different API to access that data. Now, starting all the way at the bottom of this pyramid is this storage layer. There's some in-memory caching that's allowed in Spark, so you can cache some of those different operations as there's data coming in. But generally, your data lives somewhere else, either on a cloud storage bucket or a server somewhere. So generally, you can keep that storage in a very cheap storage system and then leverage some of these memory optimizations within the processing system. From there, there's the execution engine that actually runs the different processes and schedules them, and then the resilient distributed data sets that have some of these controls for the distributed data layers. Finally, all that bubbles up to the highest level, which is the level we're working at today with Spark SQL and Dataframes that allow you to process the data either in a Pythonic API or with Spatial SQL, which we'll show you both options for. Now, one of the key strengths of Apache Sedona is the functionality that is stored within the library. It's probably second to only PostGIS in terms of the volume of spatial operations that it performs, up to over 300 as of the recording of this video. And there's a few different pieces that are inside of that broken down in this chart here. First, there's a large number of vector operations to work with point line polygon data, both two-dimensional, three-dimensional, and four-dimensional if you add a time component in there. This allows you to do different processing operations to manipulate geometries at scale or perform things like spatial joins and understanding spatial predicates like bounding boxes and relationships, as well as different distance functions, measuring k nearest neighbors, and a number of different operations to manipulate and adjust vector data. Next is the raster capabilities that allow you to work with things like satellite imagery or pre-processed raster data like digital elevation models. You can read in raster data, perform map algebra, you can adjust and create raster data within the ecosystem, and perform things like zonal statistics, which cross into using vector and raster data together. In terms of core use cases, there are also some spatial statistical functionality like Geddes or G star and others, which we'll go through very briefly, that you can use to generate features for machine learning pipelines and perform general operations for spatial feature engineering to consume in machine learning workflows or even process data to be used in LLMs and AI applications. Finally, there are spatial optimizations that allow you to do things like spatial indexing and spatial partitioning to functionally split up your data to make it very effective. We'll touch on that very lightly today, but there are some different tools to allow you to do that. Now, generally, a Sedona leverages a Lakehouse architecture. Now, Lakehouse is one of a number of terms that revolve around different data setups and architectures. First is a data lake where you basically dump all of your data into a storage location. That could be your local computer, or that could be a cloud storage bucket. A data lake by default is unorganized and unstructured, so there are some different issues with that. Now, a data lakehouse allows you to add some different functionality on top of that to integrate and store that data more effectively. And when you add a system like Apache Iceberg that allows you to add a table-based structure on top of your data that allows you to do a number of things like track history changes, schema evolution, and more. So looking at this stack here, you have your object storage that you're storing your data in. When you generally, the best way to work with data in Apache Sedona is with GeoParquet or with cloud optimized GeoTIFFs or even a stack catalog that allows you to read a number of different raster data sets over each other. But generally, these cloud optimized formats will make it really effective to work with your data at scale. From there, you can add in a table layer like Apache Iceberg to effectively add some data controls, data schema evolution, snapshots, and history within your data set as you're writing and working with that data, rather than just using flat files themselves. And then all the way up to the top layer where you're running your analytics with Sedona plus Spark. In summary, when would you choose Apache Sedona? Well, first you want to evaluate your data. If your data is increasing in volume, and there's no like hard limit in terms of the number of gigabytes, but I generally say 30 to 50 gigabytes, somewhere in there, then there's a good time to consider using Apache Sedona for processing that data. On the flip side, that could also be in the high millions or billions of features when you have data at that scale that you need to work with and process. You also need to assess your technical resources, understand that your team has access to a Spark cluster or understands how to connect and stand up Sedona with a Spark cluster is important. We'll be doing that locally today to get a quick preview of what that looks like. I also recommend starting with simple workflows, understanding how that works, and effectively developing a proof of concept that you can work with your process and structure in Sedona. This tutorial will walk you through how to do that locally, so it'll be an easy setup to get you started on a certain volume of data that you can test and run. So this video will help you get to that step quite quickly. And then from there, you can scale incrementally. Once you've done that, you've understand that Sedona is the right fit for your problem. It's super easy to scale up and go from there to leverage different partitioning processes and then ultimately move that into a cloud-based workflow. So before we begin, I want to take a quick look at the Apache Sedona documentation. You can see that here as of the recording of this video. This gives you a little bit of an idea of the different things that you can run with Apache Sedona and then some of the processing speed as it compares to other different systems. What I recommend checking out is the API documentation. This will give you a quick view on how to do that with different functions such as vector data. You can look at the different functions that are available here. There's some visualization tools that are built in and some raster data as well. You can look at the raster functionality here. You can always search if you want to find something there as well. I also recommend checking out the community. There's some different places to connect with the Apache Sedona community, such as Discord and others. So make sure to check that out. It's an open source project that's very active. So if you want to get involved with the GitHub or on the Discord, I definitely recommend checking those out. And then there are some programming guides here that walk you through some of these different pieces in detail. I also have a tutorial on my blog here if you want to go ahead and check that out. There's some different steps that we'll be actually going through today to show you exactly how to do this, and we'll walk through this entire process in detail. We'll go through two different workflows. One is setting it up on Docker, and then the other is setting it up locally using Java Java. I recommend using the Java workflow because it'll be using your machine resources a little bit more effectively. So you can go ahead and try that. And the Docker one is pretty foolproof. So we'll start there just to show you what it looks like on Docker, and then we'll move into the local setup as well. But we're going to start with installing the Docker-based version. That's pretty foolproof and will work on any system. Now, the problem is you're limited to the amount of resources that you give to Docker. So that's one thing to be aware of. If you go here, you can see that there are some different settings in the Docker engine. So you can basically allocate and structure the resources. I have them pushed all the way up so I can use kind of as much as I possibly can within the Docker system. So that's one thing to be aware of, is you need to adjust these settings and resources if you need to add more computing power to that. But with that said, the process to set that up is actually quite simple. After you download Docker, you can go to docker.com, and then you'll see the different Docker install options here that will allow you to install Docker, and you can set up any kind of containerized services there, which is basically, if you're not familiar with containers, it's like a separate environment that lives on your computer. It's completely walled off to anything that's installed on your computer. So it's a blank slate, and it'll only install what you tell it to install. So to do that, once Docker is installed, it will install the command line tools, so we can go ahead and get started by running these commands. So the first one we want to run is docker pull, and we'll pull in the latest version of Apache Sedona. So I'm going to do that here. I'm using VS Code as my editor, and then I'm just going to run those commands down below in the terminal here. So we'll do that, and you'll see here it will download that version, and we'll tell you all the different pieces it's downloading. And then once that's all done, we can get the actual container up and running. Okay, so now that that's finished installing, I can go ahead and run this command. So you'll see that there's the docker run command, and then we're giving it a few different options here. So the first is that we'll have a driver memory of 6 gigabytes, executor memory of 8 gigabytes, and then we're binding a few different ports here for the different things that are up and running. So that's what it'll do, and then it will run Apache Sedona latest. So you can go ahead and run that command. If you do get an error, it's likely that it's because you need to allocate more memory in your Docker machine. So I showed you how to do that before. If you just go over here to settings and then resources, you can allocate the appropriate tier that you need to have. So that's your disk usage, your CPU, and just bump those up till it run. And once that runs, you'll see that it will pull a new container name. You'll see it'll have the image of Apache Sedona, and then all of the ports that are it's bound to there. The one that will get you access to your notebook is your local host 8888. So if we go back to our browser here, you can see that now I have a Jupyter Notebook up and running, and that is connected into the Spark instance that I set up. Now you'll also notice that if I go to localhost 8080, I actually get access to the Spark system that's running here. This is where you can kind of see the backend processes and things that are running here. So you'll see the worker applications that are running, completed applications. So if you do want to track this there, you can see that. But overall, will get you set up, and then you can actually start running notebooks in here. So that's the Docker setup. That's your kind of quick and easy setting to get up and running. Like I said, there are some memory constraints. So it's using the virtual machine, not your actual computer. So I actually prefer to run the local setup myself, and that's what we'll get into next. So one final note, if you do want to keep this up and running, you can. Otherwise, if you just hit stop, you can shut it down, and then you can do that. If you do delete that, you'll lose everything. So you kind of have to start from before. So if you load data in or stuff like that, that's just one caveat to be aware of there. Okay, so now we're going to set up and run our local instance of Spark. And to do that, that requires Java. Now, this is one thing that always tripped me up when I was getting up and running and testing Sedona, was installing Java. But thanks to some folks that I work with, they've shared an easier way to do that. So that's what we're going to go ahead and do today. Okay, so now we are going to pivot into installing Apache Sedona with what's known as SDK Man, which is a SDK or software development kit, will allow us to install Java, which allows us to run Spark locally. So this is skipping over all of the Docker stuff. And the Docker container, like I said, works well. It's kind of one contained thing. There's no extra setup. But I find that this gives you a little bit more flexibility. You can use in your own development environment. So if in this case, I can use VS Code to write my code and view my code and do all those different things. So it gives me a little bit more flexibility, and it doesn't have all the same constraints of like the virtual wrappers of compute performance and stuff like that. So I think this is just a little bit of a faster approach. The first thing you want to do is you can grab this repo. This is a GitHub kind of tutorial repo for this. So this has like the notebook and all this stuff. So you can go here, grab the Sedona tutorial. You can use this command to just install and download that. If you need to install the GitHub CLI, you can check that out here. And then you can always just download it with a zip file as well if you want to do it that way. So that's all kind of there. I promise I'll have a README up and running by the time this is there. So you can actually download that. And then there should be instructions to actually install everything. So I'm just going to clear out of here and make this a little bit bigger. And then you can actually see that there's the Docker instructions and the local instructions here. So that's what we're going to do, the local instructions. So let's clear this out and take a look. So the first thing is I have to do is install that SDK, man. I had it installed and I uninstalled it just so we can, all see this from the beginning. So that's what we're going to do. So it's just this command to curl, which is to grab this URL, install it. So I've set up a shortcut where I can actually just a command to run this in the terminal window below. If you haven't used VS Code before, I definitely recommend checking it out. There's this section up here that allows me to add a terminal. There's the co-piloting features. That's the files over here. And then this is the terminal. So I can write code in terminal there. You can just copy and paste this as well if you want to do it that way. But I kind of like doing it like this. So I can run that. This is going to install SDKman, which is pretty fast overall. So it should be a quick download. And then what you want to do to run this tutorial, there's a specific version of Java that I'm going to install, which is this 17.0.13-Zulu. So I'm going to install that. I might need to restart the terminal window there. So let's go ahead and try that. And yeah, that was the case. So just be aware that you might need to start a new terminal session just to get the download like up and running. So we'll do that. That's installing and we'll let that run here. And that's all set up. So to confirm that that worked, we're just going to see Java version. You can see that it's that version that we installed and everything here looks good to go. And you can see exactly where it installed here. You can see it's that SDKman version. And then that's all set up. So that's step one. We have Java installed now, which is great. And then now we just need to install all our libraries to support Spark and everything like that. So that's what we're going to do next. So let's just clear this out. Oh, type below here. If I just type clear, I can get rid of everything there. And then what I want to do is install, I'm going to use UV to actually install all of this stuff. So you can install that a few ways. You can install that with pip, or you can install that directly. But first of all, let's answer the question, what is UV and why should I use it? So this is the repository. You can go to the docs here. It's just a very fast package manager to install Python libraries. So it replaces all of these things like virtual environment, Py environment, pip, pip-tools, pip-x, all those things, and it's very fast, right? So those are the biggest advantages. There's a bunch of other stuff here. You can see it works on all different platforms, but that's probably the biggest reason. And this is all written in Rust. Rust is very fast, and it's fast becoming like a backend to a lot of different things. So that's like the good news about that. So that's what we're going to use. You can install it with pip, ironically, or you can just install it by the command line. So I'm just going to do that. I'll go ahead and install there. Everything's installed. The commands are shadowed by other commands you can see here. And then what I'm going to do is I'm going to install this pyproject.toml file, which you can see here. This has all the stuff I need to actually run this. So we have, Sedona Kepler, GeoPandas, PySpark, setup tools, all these packages, kind of like a requirements.txt file. So you can see here what that is, and we'll go ahead and run that. So let's go ahead and do that here. It's going to install everything, which I had installed already. I did not uninstall that stuff, so that should be there. And then we're basically ready to get up and running. So PySpark is up and running. We have Java installed, we have Sedona installed, and then all of our support libraries there as well. So let's go ahead and do that. I'm going to basically use this UV run command. So that's IPython kernel install user and call it Sedona demo. So we know what that is. So that's all set up and running. And then I can actually run a Jupyter Lab server here. So I'll go ahead and run Jupyter Lab server. And I just want you to note these URLs down here. So if you see this localhost 888 or the 127, I just want you to copy that just so you can see this. It actually is running over here. So if I copy this into the browser, you'll see that it's, you can run a Jupyter Lab server just like this if you want. I'm going to show you how to do that in VS Code here as well, so we can get that set up. So to do that, let's just save this, get rid of that. I'm going to open my notebook. So it's this Apache Sedona tutorial. We'll get rid of our command line for now. and we'll just back this out here. And then what I want to do is select, go to here. You'll see if you have that, there's some extensions here you may need to install. So if you look over here, there's extensions. I've installed Jupyter, so there's some extensions. There's a lot of different ones you can use, but there's different ones that I've used before. So you can see all the ones that I've installed, but Jupyter is the one you need. And then you'll have some of these different things here. So I'm going to select the kernel that I want to use. I'm going to use an existing Jupyter server. So that last command I used set up the Jupyter server. So I have one already. I don't need to start a new Python environment. I don't need to start a new Sedona kernel, or sorry, Jupyter kernel. So I'm going to do that here. And you see these are ones I've run before. These are all, I don't need these anymore because I've shut these down, but you could even connect to something in the cloud here and stuff like that. So it says enter the URL of the running Jupyter server. That's what we set up before. You can give it a name here. So this is tutorial. I can hit enter, and then you can see here that it's that Sedona demo that I've set up before. So these are the different options that you have. And you can see here, this is the Sedona demo, Apache Sedona tutorial, last activity 1 minute ago. So we'll go ahead and connect to this that's up and running, and we are ready to go. So now we can actually get our first step, which is connecting to our Spark server and connecting everything there. So there's a lot of stuff happening in this first step. It's kind of like your imports, but doing that on a Java side. So I'm just going to go ahead and run that to show you what that looks like. It's going to connect, and there'll be a pretty long output here of a bunch of things. So it'll look like something went wrong, but it didn't. So there's just a lot of these things. You can set that to a scrollable element. You'll see here this kind of like table that generally means that you're all set up. So what happened in all these different things? That's probably what you're asking here. So you can see I'm just importing the Sedona Spark context here. It's allowing me to connect the Sedona to the Spark context. And then I'm setting up a few things. The first is these jar packages, which are basically like Java packages. So I have one for Sedona Spark, one for GeoTools, which is something that Sedona uses to run some different operations. And then Hadoop, which is allowing me to connect to my files system and things like that. Hadoop is kind of the simple way to put it, a predecessor to Spark. So there's an easy way to do that. Then there's some different jar repository components that we get in here. And then everything else here is more configuration. So I'm allowing that Hadoop to connect to an S3 file system. I'm going to allow it to connect to read anonymous data sources. So things like open data, AWS portals generally use anonymous credentials. So that's an easy way to connect to that. So I'm just telling it, yes, connect to S3, use anonymous credentials. There's different tutorials you can use to connect to some different things like Source Cooperative where there's some data on. But we're doing most things locally just today, just to keep it simple. And then you're basically, just as you saw before, there's the shuffle partitions, which is your partitioning on your machine, your driver memory, and then your executor memory. So that will allow you to add memory, just like we had in the Docker command, a little bit more that you can have to get set up there. And then we pass all of that configuration components into the Sedona context, set some limitations on what we want to actually interact with there, and then we should be good to go. But just to check that everything's working, we'll do a very simple example. So there's about 15 parts, I think, in this tutorial. So we'll go through each one and just kind of walk through the basics and add some increasing levels of complexity from there. So the first thing I'm going to do is I'm going to create a very, very, very simple data frame from there. So I'm going to import from PySpark this function row, and I'm going to create a very basic data structure. So inside of a list, I'm going to create an object row that has an ID of 1, name of point A, and then a latitude and longitude. So I'm going to do that 3 times over. It's very similar to if you're creating a data frame from complete scratch in Pandas or GeoPandas, and you're doing that with a dictionary. So same type of process here. We're doing effectively the same thing. So we'll go ahead and do that. And then we're going to tell Sedona to create a data frame from that data. And then we're going to use this command .show on the data frame to actually show that. So we'll go ahead and run that, and it will show our data frame here, which is exactly what we expect. So that's the first thing. We've just created a Spark data frame, nothing too groundbreaking here yet, but that's what we've done. And what we actually want to do is, you can see these are latitude and longitude columns. So these are just float values, with decimals and things like that. So we actually want to turn that into a geometry. Now, there's these SQL-like operations with PySpark. You can see here from PySpark SQL.functions, I'm importing this thing called expr or expression, and that will allow me to add a SQL-like function or a SQL-like expression as a column to do that. So you can use a Python, this kind of like combo Python plus SQL kind of, different structuring here. So that's what we'll do. So we're going to actually turn this into a geometry, proper geometry, and use a function from Sedona here called stPoint. So stPoint will turn that into proper geometry. So on the data frame, you're calling this function with column, which will add a second column. The first argument is the name of that column, so we'll call it geom. And the expression here, we're wrapping that function expression and passing it as a string, this SQL expression. So we're saying st point. We're going to cast the longitude as a proper decimal. So just to make sure everything's the way we want it, and do the same for the latitude. So st point takes the longitude and latitude in that order and creates a geometry from that. So that's what we're doing here. That will allow us to do that. And we can show the data frame here. And we're passing in one argument called truncate false, which would not, if we don't pass that in, we'll cut off the different things. And you can see here now we have a geometry. We have a WKT geometry point for these three different things. And that's exactly what we wanted to do. So we've just gone through those basic steps, creating a data frame from the most basic fundamentals. Most time you'll be reading it from a file. And then now we have a proper data frame here that we've set up. Now you can also do some just pure SQL-like queries. So like I said, I'll be showing examples that are very Pythonic structure and some that are very SQL-like function. And then the nice part is you can move in between those. In a GeoPandas, you're kind of stuck in the pure Python workflow. If you're in DuckDB in Python, you're stuck in the pure SQL workflow. So this gives you a nice kind of balance between the two, depending on what your programming preferences are. So what we'll do here is we'll create basically a polygon on the fly from geom from WKT. WKT is what's known as well-known text, which is just a representation of a geometry. You can have many different types of geometries in well-known text, such as points, lines, polygons, and then different structures for these combined geometries and stuff like that. We won't get into all of that today, but there's basically two representations of geometries that are not, if you're using just vanilla Spark, you can use well-known text or well-known binary. Binary is the other option there. So you can use either of those two, and sometimes you'd have to use these functions to translate those into proper geometries. You're running this in a different setup. So Sedona is the one that actually provides these functions just to turn well-known text, well-known binary into a proper geometry. And then we're just wrapping that in another function called area spheroid. There's st area spheroid, I should say. So st is the common term that is used in the front of all spatial functions across all spatial SQL. It stands for spatial type. So you'll see that. And if you see st, you know it's a spatial function. And there's a function called st area, which will do it on a flat surface. Area spheroid will effectively try to approximate that to the spherical surface of the Earth. So that's what we're doing there. We're just creating that as a string, and then we'll actually run that here. So to do that, you have Sedona, which is, if you go all the way back to the top, Sedona is that engine that we've created here to run everything that we have. So that's what we're doing there. And then we'll run that query against that, and then just quickly do the show operation to see what that looks like. And you can see here that the area is 2.01. And that's correct because it's in decimal degrees, not a different projection system. So if you're brand new to spatial data, you probably know things like latitude and longitude. That's in a decimal-based system. So the area of there is based in decimal degrees. If you use an area-based projection system, and we'll look at that using some different functions like S-tree transform, you can measure things in meters, or there are even projections that measure it in feet and different things like that. So that's one thing to be aware of with spatial data is you probably need to run this transform function, because if you're seeing, hey, there's measuring the area of something like New York City and it's returning like 1, that's probably why that's the case. Now we can also do some spatial filtering. So once again, I'm going to create this data structure here, create my data frame. I'm going to recreate that and cast that as a latitude and longitude. And then what I'm going to do at the bottom here, this is stuff we already did before, so I'm breezing through it quickly, but we can create or replace this view. And a view is like a database view, right? Same type of concept where you have a view of a database. It's kind of like a table, but it's temporary. It's constrained to the context that's running in the notebook. So you're not actually creating a table. It's just sort of referencing that this data frame can be used as a shorthand, be named points. So dfgeom, create replace view, points, and I can treat that like a table in a SQL query here. So what I'm doing here is I'm basically saying, here's the ID, the name. I'm going to translate the geom back from the actual geometry into text. So I'm going to show that as text, as well-known text from points. And then I'm going to run this operation where st within. And this is what's known as a spatial predicate to understand relationships. So imagine that I'm creating this geometry from text, which is basically like a box, right? And then in that box, I'm trying to see which points fall within that. Now I've set it up so 2 fall within, 1 does not, right? And so I'm basically going to use that as a where query to do the spatial filtering. So I can go ahead and do that. Go ahead and run that here. And you can see here that point A and point B within that box, and point C is not. Right. So there are some like spatial, like there's some special things within these filters, and we can refute the documentation with that. So if we go to programming guide, or sorry, into API docs, vector data, and predicates, you'll see the different options here. So there's within intersects, which is like if it even if it just falls in the line, it will count it. If it's outside of that, you can use disjoint to see if it doesn't fall within that. So if I was just to change this to st disjoint, I should just get C, which is what I was expecting there. And now if it falls exactly on the line, I use st intersects. It's the most common one because it gets anything in or touching. You can get that there. And then there's a bunch of other ones here that are within those predicates. So it's just something to be aware of if you're writing those different things. Now, as I mentioned, we can do all of this as Python-based structure. So you can see here from sedona.sql.st constructors, just like I imported that expr, that expression function, I can import these as Python structures too. So geom from text, st as text, st within, and then I just have this lit or literal, which basically turns the text into a text value from Python into a literal in Spark. So just a little translation there. So what I'm doing is I'm setting up my well-known text polygon. I now have this function that's going to capture the geometry here. And then I have the literal, which translates the text into the literal. And then what I'm going to do is have my original df geom, which is this table structure here. I'm going to turn that and basically say within, set up a filter, just kind of like a where clause. Use st within, and then get the geometry from the data frame, and then pass my polygon geometry, which I've set up as a Python object up here. And I'm going to run a select operation. So I'm going to select the ID, the name, the st as text geometry, and then give it the alias of well-known text. So you can see this is all Pythonic here. It's the same thing that's going to run. Oops, I did not define st within. I should have run that cell. That would have helped. And then now it's the same result. So it's really how you want to write this. If you're really, really kind of like functional with a Python or a Pandas API, this might be the way to go. If you're used to writing SQL, that's the way to go. So it really depends on what you choose and how you want to write it. But it's nice that you get both options that are set up there. Okay, so now let's read some real data, which is probably a lot of the times what you'll be doing. You'll be having some tabular data. And there's lots of different ways you can import data from Sedona. So there's a lot of these constructors, and you can read these in as different data frames. So there's options for things like GeoJSON. So you can actually read in GeoJSON here, create a data frame from that structure. There's GeoPackage, GeoParquet, CSV shapefiles, and then stat catalog, which is a raster reader. So we'll go through all of these in detail just to show you the different types that you can read in. So what I'm going to do is basically read in here. If you download the course files, you should get access to that data. So you'll be up and running and ready to go. So all that data should be over here. And this is mostly data from the Seattle Open Data Portal. So if you go to the course page, I'll put a reference into all the data sets if you want to check those out. But everything here is from the Seattle Open Data Portal. So that's what we'll be working with in terms of data, all data in Seattle. So I'm going to go ahead and run that. Now you may have to add some like absolutes into this depending on specifically where the server is running. So you just might want to adjust that. So I actually have to go out a level because my server is actually running in this Sedona examples repo. So I have to go out and then into the data. So that's just one thing you may need to do there. So to fix that, if you're following me verbatim, there's a data folder here. You can just rename that briefly as _data. And I'm just going to drop this into the Sedona examples repo. And then I should be good to go there. And yeah, everything's set. So if you do follow that example, otherwise you can just use the ... to back out to a different folder. So I've read that in, and now I have my geo data frame. Or sorry, my geospatial data frame or my Sedona data frame. So I use Sedona.read format, pass the format as GeoJSON, and then I load my path. And you can see here I print out my schema, and you can see the different thing in there. Now it's nested GeoJSON, so that's kind of a tricky thing with GeoJSON is you actually have to like move that into a true tabular format. Basically, everything's nested at these higher levels. There's one geometry record and then contains all the geometries, one property record and contains all the properties. So we're going to fix that. We're going to basically pull that out using the expressions as well again. I'm going to read, so I'm going to do this whole operation in one shot here. So I'm going to read the geo data frame here, read the Sedona data frame as a GeoJSON. Too many terms there. And then what I'm going to do is first use a select expression. So I'm going to select, I'm going to explode the features as features, which basically blows that out. I'm going to select the features dot star, and then I'm going to go with column and turn each of these individual things into their own columns. So the object ID, the neighborhood, alternative names, and then I'm going to get rid of the properties type, which I don't need here. So then I'll have one single entry per row. I can do that. And now I can see my GeoJSON data frame here. Here's each thing as an individual record. If I hit .show, it would show each of those things as an individual record. Just for demonstration's sake, you can see here, here's each of these individual things. So there's like these macro level neighborhoods, the neighborhood, and then any alternate names. Sometimes these names have alternate ones as defined by the city. So that's what we do there. And then I can actually do some very basic operations on these data frames. So by calling .count, I can see the number of entries, which is 94 here, which is perfect. So that's what I'm going to go ahead and do from there. Now I can also read in data frames from a geo package. And that's another nice thing that I can do here. So I can actually do a few different things. GeoPackage is a very specific type of geospatial data. You may come across it. Sometimes it's there, but it depends. So if it just as a show what it is, you can do that. There's two operations here. So I can actually see the metadata. GeoPackage contain many tables, right? So you can see here I have, the table name is parks. So there might be more than one table here, and it has some basic information about that. But you can actually read in those data frames here. And then since I know the table name is parks, I can go Sedona read format geopackage. The option is the table name of parks, and I can load that here, and then I'm ready to go. And I can see here's all my different parks. So I have my ID, my geometry, all the stuff I care about from that perspective. You can also read shapefiles. Shapefiles is a really common data type in geospatial data. It can't scale to large volumes, even though some people have pushed it a little bit further than they probably should, but you can actually use those here. And now I have a shapefile data frame. It's the same exact data, nothing different, but it's something that you can use if you come across that. So once again, just like a GeoJSON, I'm reading that, and this will actually work just as without any different operations here. So I can hit show, and it should show all of the different parks. Same data here as the geo package. So no different there. You can use whichever one you want. From here, you can also load CSVs. So this CSV is a data set from Kaggle that has historic home sales in Seattle. So it has the home sale price and a bunch of other features about the home, bedrooms, bathrooms, things like that. So we'll do is we'll pass that in here. We'll read that as a CSV. Spark is perfectly fine at reading CSV, so you can do that. But you can read that in Sedona. But as you'll see here is that there's a few different things. Is that when we have this header row, that's not data we need. The header's down here. And then we had latitude and longitude, so we need to turn those into proper geometries. So first things first, I will read that in. I will set an option header true. I will tell it to infer the schema. So guess the data types that are in there, and then load that. So just a few different options when I'm loading that in. There's very similar to a pandas type of process here. So you can see here I have these different things, and then if I went print schema and I just wanted to see the schema of the data, it should have guessed the data types, which it looks like it did a good job of there. So we'll just flip that back for now. And what I can do now is I'm going to import, basically do a expression. So that select expression allows me to do a select type, basically add a number of columns just like I would in SQL. So I'm going to select star, and then I'm going to do st point longitude, latitude, and set that as our geometry. We'll do that. Nice part about Sedona is that I can just run this and it won't execute until I actually call a command like show or count or something like that. So I go ahead and hit show here, and all the way at the end, I should have my geometry, which it looks like we did a good job of there. And then to just see the number of records, I can hit that and count. And you can see here that there's just shy of 600,000 different records of home sales in Seattle during that time. Okay, so moving on, now we can read GeoParquet. Now, GeoParquet is usually, it is a cloud native format that makes data, especially working with distributed systems, a lot more efficient. You can partition the data and do a lot of different things. This one, I've just created a single flat Parquet file, which is probably the least optimal way to use GeoParquet, but just for example's sake, we can go ahead and do that. All I had to do there was read that in, use format GeoParquet, and then load that in. Then you can read partition GeoParquet data. You can read Parquet data on a cloud bucket. This is really where it starts to get really scalable and extensible. But the nice part is I can read your legacy formats like a shapefile and GeoPackage and put that right alongside a cloud native format super easily. So this is just bike paths or bike infrastructure in Seattle. So that's what I can do there. And then now we'll look at and actually take a look at the projection, which is stored in this SRID, spatial reference ID. And you can see what that looks like here. So there's a function I can actually see, okay, here's what it is. And I can see that it's the it has not been set on this file. So what I can do is I can use st transform. I can pull it from one format to another, and then I can actually translate that. And then you can see here that it's translated that into the correct format that I want, which is 4326. Right? So you can actually set that up and do that. So 4326 is your basically the format that you use for your pure lat longs. If you want to do measurements, that's why I'm adding this. The 2920 is the one that we'll eventually use, but you do have to pass an operation here to do that. So if I pass like 0, it'll freak out because it doesn't know which one that is. So I just have to pass something in there and then turn that into 4326. So the last one here that we'll be using a little later is the public school sites. So we'll see here that these are all the public schools that are in Seattle. Now we're going to move into working with some raster data. So raster data, if you're not familiar, really comes in two forms. It's gridded data, right? So this is data about the Earth that can't be well defined by boundaries. So things like temperature, you can't clearly define it by a boundary. It changes. Things like elevation are constantly changing. So it's not like a discrete thing. It's kind of something that's constantly in flux. And it's pulled into raster. And if raster might sound familiar, that's because it's like an image basically. So it's because we have satellites orbiting the Earth. They collect data. We use that data and we kept it in an image format. So if you're coming from outside the geospatial world, if you're hearing these terms for the first time, you're like, oh, raster, that sounds like a pixelized image. And you're right, because a lot of that data is stored in what's known as a geotiff. So it's a georeferenced TIFF file. It has pixels, and those pixels contain values. Sometimes it's one value. In the case of elevation, it's the elevation in wherever that pixel contains. That pixel might be 1 meter, it might be 30 meters, something like that. And then you also have what's known as array-based data. So a common format for that is known as netcdf. And that is basically a combination of lat-long grids and then a timestamp. So that could be changing temperature, that could be changing water temperature, stuff like that. So we're going to look at both. Sedona supports both netcdf and some different raster files. So let's kick over to the docs to take a look at that really quickly. So when I look at raster data, you can see here's the types of raster data that supports. There's the geotiff, you can make empty rasters, and then there's netcdf. There's really kind of core two functions for netcdf. You can load that in, and then you can get info about that. So that's where that comes in. We're going to look at the netcdf first, but most of the data generally is going to be working with geotiffs here. So that's kind of where you're traditionally be working with that. So let's take a look at netcdf. I have this data, which is data. It's like, I think, water temperature around Seattle. We're not going to really use it for much right now, but we're just going to take a look at it. So you can see here, I'm loading this in. I'm going to read this as a format. It's called a binary file. So you're going to always read it as a binary file format and then convert that to a true raster. So let's read that in. And you can see here, here's the path, here's the modification time, and the content, which is in binary. So it's not like tabular data. You can't see like, oh, here's this pixel grid and here's that. It's kind of just you're referencing a file and then you're getting data back. So it'll feel weird. It's not like tabular data if you're coming from that world, but you'll be able to read rasters and then do interoperable operations we'll get to later in the tutorial, which is the fun part of all this. So what I'm going to do here is I'm just going to quickly explore it using and turn that into a proper raster file and extract the data and the latitude, longitude. So you can kind of see here that I have to know, if we go to this here, from netcdf, you need to know the content, kind of the information about that. And that's from this netcdf info, and you can get some information about that. So we have these different, what's known as like basically bands or chunks of data. Ours is contained in something called data, but they might be letters and things like that. And then you have lats, longs, and stuff like that. So what we're going to do is we're just going to do that. The repartitioning allows us to do that and do that pretty efficiently. And then we're going to turn that into a proper raster file and see and take a look at what that looks like. So that's what that is. Now I have the netcdf data frame that is actually in a raster. You can see that here, grid coverage 2D. The content is still there, and then we've extracted that. So now I can use that to actually reference it and pull that against a latitude, longitude. I'm not going to go further with this data because this is more of an edge case, but I did want to highlight it in case you're working with climatic data and you come across, well, what's this netcdf thing? How can I work with it? But most data is going to come from what's known as raster data. So we'll open this over here and take a look at what this is. So this is a satellite image. It's collected from Sentinel-2, which is a mission, you can actually look at that, from the European Space Agency. So they have these satellites here, and they're flying all over the Earth and collecting data constantly. And this is just a catalog online that allows us to look at this data. I'm looking at one specific image. This image was created on April 24th, 2025, and is taken at 4:46 UTC. And these data, they're constantly scanning the Earth and collecting information about the Earth. This is what it is. And you can see here that it is, basically, we'll just make it larger. You can see here that I think this is 30-meter resolution, but you can see here's Seattle. Here's the image. And if we zoom in, you're going to start to see some features start to come into clarity, but it's not perfect. We'll try to get that. So I'm in Seattle here. I think this is the stadium where the Seahawks play, the American football team here. But you can see as I zoom in, it's not super high resolution as you would expect from Google Maps, right? This is data that's used for a lot of different things. Some of that might be looking at, vegetation indices. So you can see here that there's some greens and stuff like that. And this actually contains multiple bands of data, which we'll take a look at as well. This is what's known as the true color image, but there's a band for blue, cloud probability, there's near infrared bands, 3 of them, red edge, snow probability, there's true color info, aerosol optical thickness. All these different bands are all collected from the same satellite image, right? And this is all parts of the image that we care about. And using that, we can do some different analyses. So it's not used for very detailed things, can be in some cases, like, you can start to see where there's buildings here, but if you get into other areas, it's going to be a little bit more difficult. But that's kind of what we're using it for. So it's not like your Google Maps high resolution imagery. You want to see my house. It's a little bit different, but that's just to give you an idea of what that is. But this is one tile of one snapshot, and this is coming around constantly. And you can see there's some different things here. Like you can see should be cloud shadow percentage, vegetation percentage. There's all this stuff that's automatically collected from the data. If we zoom out at a very high level, you can see some different stuff. I think this is like Mount Rainier or something. Yeah, Mount Rainier down here. You can see all that stuff. So that's kind of what a satellite image is. So we are going to read that in. So I have that here. That's like one example of an image. Here's another one that's also kind of interesting. This is a land cover data set. So they also produce processed versions of this data, and this is land cover. So they basically take that, perform some machine learning on it, and they produce this land cover data set. And I don't know if it's going to show up here. We'll see if I can zoom in and get it to render. But basically, this will classifies the world to 11 different classes of land cover. So if I just Google that quickly, world cover, sorry. This is what that looks like. And it's a global data set, maps it into 11 different classes, but don't quote me on that. And you can see here, if we zoom in, this is the entirety of the data set, and we can actually access that as raw data. So you can see here, there's tree cover, shrubland, cropland, built up, snow and ice, permanent, water bodies, wetlands, mangroves, stuff like that. So if we go up to Seattle here, I can go, should be right here. Here's Seattle. You can see a lot of it is urbanized. There's built up areas, sparse vegetation here. So you can see what that looks like. And then obviously these different areas. So you can see where that's kind of classified. There's this farmland down here. So if I move over to other parts, you can see this is a lot of farmland. And I believe this is at 10-meter resolution. South Florida is probably the most interesting because you have this massive wetland area, your roads, stuff like that. So it gets a little interesting once you get down into South Florida. I always like looking at that just to show the diversity of the data that's there. So we're going to read in one tile of that. And this is coming from, they host this data free for everyone to use. And I've downloaded one single tile, and we'll load that in, and that's going to be our data frame. So the first step is I have to turn that into a binary file. So this is my raster data frame. And then I'm going to add a column that extracts that from the content. So from that binary, I create the raster column, and that's what's here. You can show it if you want, but we'll skip over that. And to make it efficient to read, we're actually going to split that out into a grid of tiles, right? Since these images can get quite large in terms of the scope, we're going to split it into tiles of 256 and 256 tiles using this tile explode methodology. And that allows us to create multiple ones. And what that allows us to do is quickly scan, okay, if I'm doing an intersection to see if this feature falls within that, I don't have to scan the entire image. I can just find the tile and say, oh, I just need to look in this one tile, and makes the data a little bit more efficient. So that's what we'll do here. You'll see as this gets spit out what that looks like. So it'll actually turn that into like rows of data, each one representing one tile that we've created. So now I have this grid, and this is a grid of 0, 1, and this is my tile here. 1, 0, so on and so forth. So it looks like, can't see because I made at least 20 down and then however many across, and it'll split that appropriately. Each one should contain 256 by 256 pixels. So that's it for loading in raster data. We'll explore that more, actually intersecting with vector data, because it's hard to do a lot with this unless you're really deep in this world, but there's a ton of value in this data. I definitely recommend, if you're interested, checking out AWS Earth, or Earth on AWS, sorry. There's a registry of open data data on AWS, which you can take a look at here. So it has Sentinel-2. It's all hosted on S3, so you can take a look at that and see there's just a ton of stuff here that you can use. So definitely check that out. This is a new area for you. So this will be a quick section, but so far we've done everything kind of operating in data frames and working with data there. And now you probably want to understand, can I actually see what I'm looking at from my data? And yes, you can. So there's some functions here that allow you to do that. So jumping back into the documentation, if you want to take a look at in the raster and vector section, so there should be visualization here. And there's some options. I actually like the Sedona Kepler version that basically ports in a open source library to create map dashboards called Kepler GL. And so you can install that. We installed that specific functionality when we did the install with UV. So that's already there. And then for raster data, you can visualize those as images. So you can see here what that looks like, and then you can get a nice little image of that. So quick section on that. What we're going to do here is import this from the Sedona utils. And what we'll do is we'll create an HTML data frame from our raster data frame. So it's going to use this function rs as image. It's going to spit it out as a 500 pixel image for the whole thing. And then we'll display that here. So we can do that within the context of a Jupyter Notebook. There's some extra pieces I installed since we're just using the Jupyter server, but now I can actually see that here. And that's that world cover image that we installed. So you can see, this is our mountain ranges. I'm pretty sure this is Mount Rainier, but don't quote me on that. Obviously river down here, water. This is Seattle. This should be, I think, Portland, Oregon. Don't quote me on that. And then your farmland out here, stuff like that. So you can see here's the actual image if you ever want to go in and take a look at that specific thing. So it's compressing it and making it this smaller image. This is not the true granularity like what you saw in the interactive map. What we can do here is actually create an interactive map for our vector data sets or our tabular data. So we can do that here. And we can quickly create a map of our Seattle schools. So what this is, you can actually zoom in and out. So this is Seattle schools. You can see the point, the address, and then you can do some basic styling here if you want. You can go into this layer, and then you can kind of style that. You can change the fill color if you want. You can style that based off of a specific attribute. So if you wanted to look at, I think this is if it's like a elementary, middle school, high school, stuff like that. So you can do that here, and then you can, we'll try doing it off of a string, maybe something like that. So status, maybe that's like open closed or something. I don't know. It's actually in all that data. And then you can actually do a lot here to kind of create 3D and stuff like that. This is all kind of in the context of the notebook. So there's, guides here for the user docs. You can turn this into a 3D map and all this different fun stuff. So there's a lot of cool things you can do here with this, but keep in mind it's in the context of notebook, but just to see that data, you can add layers. I wouldn't recommend if you want to save this. There's some other tools. If you want to do some more advanced stuff, I check out something like Leaf Map, and you might need to translate data into a file or something like that. But this is just a quick, easy way to see the data in the context of a notebook as you're going forward to do some stuff like that. Okay, so in this part, we're going to move into actually working with vector functions. So vector functions are over here if we go into vector data functions. And there's a few different ones here that allow us to do different categorical things. So they're kind of organized by that. Function might be transforming data. So I can turn a geometry into what's known as well-known text. I can calculate and turn a polygon into just the boundary or the line around that. You can create a buffer. So create a point into a polygon or even a polygon and add area to it to say I want to buffer this by 100 meters. There's a lot of different functions here. So this obviously is not a course on spatial SQL and all the things you can do, but you can create 3D geometries. We can build H3 cells. You can find the length of something. You can normalize. You can simplify. So there's all of these functions, tons of them for doing lots of stuff. We're going to explore a few, probably the most used ones, I would say. This isn't exclusive to any specific use case, but these are the things that I find myself using a lot when I'm using spatial SQL. So that's kind of what I want to focus in on, zone in on those, just so you have an idea of what that looks like. So you can see here is that I can use two ways you can use these. You can use these as, once again, proper SQL, or I can actually import these as Pythonic calls. So that's what I'm going to do in this first one here. I'm going to import these as Python. So I'm going to pull stbuffer, sttransform, and stconvexhull to show you what a convex hull looks like. You can actually take a look at that here, and this will kind of create this kind of, hull or polygon around said feature or features, right? Concave will try to actually kind of compress that. So that's another one. So it's kind of like an area around that. So you can see what that looks like from a convex versus concave, and kind of get your comparison there. So that's convex around it. Concave will try to suppress that. So that's what we'll do here. So we're just going to kind of create that around that. So our first thing here is we're going to create a buffer data frame around our schools. So to do that, we'll write that in a very PySparky type of way, if that's even a word. So I'm going to import a column and my literal here. And so for GeoParquet, my data frame that contains the schools, I'm going to select wrapping in st buffer. So it takes two arguments, which is the geometry and then the buffer. So the first thing I actually have to transform that, because this 4326 projection, as we remember before, is a decimal degree. So I don't know how to measure things in decimal degrees. So we want it to be in proper format, like a meters or feet or something like that. And this projection allows us to do that. So this is that literal. I'm casting the string as a literal here twice from 4326 to 26910. And then I have my geometry column here, and then my st transform. So this whole thing will return a transform geometry, and I'm going to give it a buffer of 100. So that's what we'll do here. And you can see now this is a polygon, and then I can actually showcase that on a map. And you'll see here that as I zoom in, these aren't points. This is actually a polygon around that school. So now I actually have buffered geometries there. So I can do the same thing using SQL. So this is going to be a select expression. I'm going to, select star. Then I just basically encapsulate this as a whole thing here. That whole function that I wrote up here is now just like this. And then I'm going to drop the geometry, and I'm going to use a column rename. I'm going to rename geom as geometry. So I can do the same thing here, basically just using still some kind of Python expressions, but not pure Python. I'm writing basically some SQL here and writing a select expression. So that's kind of how I'm defining that. So there's a lot of ways to write stuff in Spark and Sedona. So you can kind of choose the ways you want to do that, which I do find nice, is you can have that, or you can just write it as a pure SQL statement, which is sort of where I'm comfortable. But I'm try for these tutorials to push myself out of the comfort zone a little bit to do some more Pythonic work. So to do a pure SQL one, what I want to do is I want to turn my data frame into a view. Right, so this is that create or replace view. I'm going to turn the shapefile data frame of parks into parks. And let's say I want to find the centroid of the park, the center point of that park, which is basically a weighted area centroid. So as you can see here, here's my SQL. I'm going to select st centroid geometry from parks, and I'll show that. So this should return a point data frame here, and you can see this is now a point, right? Do things like measure the area of the park, so I can actually measure that in area. You can see this isn't looking like decimal degrees, so I can actually get the proper area. I believe that should be in meters, so that's the square meters of the park. And then I can do something similar with bikes. So if I wanted to, since these are lines, I want to measure how long each one is. Now these could be segments of a larger line, so it's not to say like that line is contiguous. It might actually break those lines into chunks. So it's something you might need to do a group by and what's known as an ST union to union that to one single line. So it's something to be aware of. So it's at least that one chunk of the line string, right? You may need to actually measure all of those things together. This will show kind of a hull data frame. So we'll actually kind of do that ST select. This is the more Pythonic route, and create that hull. So you can see what that looks like. These numbers are going to look different from side to side. And that's what you can do there. And then this is another one, is that I'm actually found the latitude and longitude of the Space Needle, which is here. And then I'm just going to do a pure SQL kind of function here, where I'm going to select the distance. So it's st distance of the geometry from parks. So I'm going to find the distance from every park to the point on the Space Needle. And I have to do a bunch of stuff to get that in a workable form. So you see st transform, st set srid, st point, and stuff like that. So basically I hit my first function here at the lowest level, or the middle part, is my point. So I turn this longitude first, always longitude first, and then latitude. So longitude of -122 point blah blah blah, and 47 point blah blah blah. And then I'm going to basically say, since I know it's decimal degrees, I'm going to tell that's 4326. So the first thing, I'm going to set the SRID. This has no SRID implicitly, so I'm going to tell it it's 4326 to be implicit about what that is. And then I'm going to run st transform to turn it back into the foot meter based measurement. Sorry, not foot based. And that's what we'll do there. And then all I'm doing is using this function st distance from the geometry. And what's nice about this is it's not from the centroid. It'll actually find the nearest point on the polygon. So you don't actually have to do any extra work. It'll find the nearest point on the polygon to do that. So we can do that, and we'll see here's the distance from each park to that. And we could say, we could even do order by 1 and rerun this cell here. and then we should see what how far the closest park is from there. Or maybe I did that in the wrong order. But yeah, that's something you can do there to kind of see the distance, which is a common thing you want to measure. So another thing you can do is actually generate H3 cells from a geometry. So what's cool here, if you're not familiar with H3 cells, it's a method to sort of bin and grid the world into globe hexagons, right? So as I zoom in, you'll see these hexagons change. Basically, for each hexagon, it has 7 children, and it also knows the relationship. So like this one here, it knows the ones that are near it or nearby it, and it knows if they're neighbors, it knows if it's a parent or a child. So I can just see if I can clear that out, and it keeps going down to a very granular level. So let's go to a city so we can get the idea of this. So we'll go down here to New York, and you can see how granular this goes to the street level. Like this is a street, and this tiny little ID represents this very small area here, and its resolution at 13. I think it goes to 15 in total. There's, this, you can see the area at any point. So it gives you these like attributes about the cell, right? And it's what's known as a global discrete, I'm going to butcher the word, global discrete grid system, I think, something like that. That's probably not right. Or sorry, discrete global grid system there. So thank you to the H3 website for correcting me there. And this can be very useful to do some different things, especially visualization, right? If you have a lot of points, it can aggregate those into groups. You can do some neighbor calculations and stuff like that. What's interesting is if you scale up Sedona, you don't need to use H3 cells to do things like area-based calculations, because it will just do it. You don't need to do it to have distances. There's all these things you can extrapolate off of those H3 cell IDs. I really find them useful for visualization to make the data very communicable and putting it into a grid system, and then for visualization for the web. So if you need to aggregate that up to visualize it on the web, it's very easy to do that. But for distance calculation, stuff like that, you don't need that, especially when you use Sedona with a distributed system. But you can generate those, and that's actually one strong use case, is to actually generate those cell IDs from that, because to do that for a point is not very hard, but to fill a polygon, especially a large or complex polygon, you need a distributed system. So that's basically what this does. This function will, if we go to the function description in the docs, you can see here that this will return, I believe, a list of these cell IDs, which are these numerical characters. You can see that they also have the alpha numeric version, which is this 8D2A, blah, blah, blah. But there's a numerical version as well, and it will return basically an array or list of all of those. So that's what we'll do. We'll basically fill it in there at the level 8, and then we'll get this row by row, which contains a list of all these cell IDs, and then you can explode that. You can turn those into geometries. So there's some supporting functions for H3 here in Sedona. So I can figure out cell distance, I can figure out the K-ring, or like from a cell, the ones that border it and turn it into a geom. So there's these basic functionality to work with that. But like I said, you don't need all of that when you have a, kind of a powerful workhorse like this. The last one I want to show is like doing like 3D distances. So a pure distance on a line is just, from A to B. But of course, distance changes with elevation. So if I'm going up, that will be a longer line. Triangles, geometry, stuff like that. And you can actually do that. So I'm just going to create geometry from text for these 2 points for 0, 0, 0, meaning you're basically for the equator and the prime meridian cross at 0 elevation or sea level in this context, and then going up to whatever this is, this random point that I'm going to cast. And you can see that that is actually 13. So if I change this to 14, we can see that that changes and it does that 3D calculation for you. So this is really great for things like line of sight calculation. If you're looking at points on buildings, you can figure out 3D intersections if there's something blocking your line of sight, all these different attributes around 3D data. And then there's actually a fourth dimension if you're using telemetry data and stuff like that. So things in movement and cars and stuff like that. Imagine you're collecting GPS data. You have a lat long and an elevation and then a timestamp. You can actually wrap that timestamp into the geometry and do speed-based calculations and stuff like that. So that's what's known as a 4D geometry, which sounds like we're getting into some weird metaverse type of stuff, or like the Marvel kind of different worlds, but that's really all it is. So I believe you can look at the 4D calculations here. So it's what's known as 3D. So if you basically have a geometry that's lat, long, and then elevation or height, and then time or distance, and that could be a sequence you can use in that. Very versatile. It could be a sequence 1 2 3 4 5. It could be a timestamp of seconds or something, whatever you want to do there. You can kind of store that in that data, and it's very good for those mobility movement use cases and stuff like that. Okay, so the next section we're going to move into is what's known as spatial predicates. And a predicate is basically a relationship, right? When a lot of things we study in geography and with spatial data is how things interact. So does a park overlap with a school? Right, that's a question you could ask. Does a park overlap with a bike route? Is probably a better question because I don't know how many schools sit inside of parks, but there might be one. So who knows? And then, of course, how does a raster data set overlap with a park? And what does the land cover look like in that park? How much of that space is trees or grass or baseball fields or built up environment like buildings and stuff like that? And that's questions we can actually answer with the data that we're looking at today. And you can kind of start to imagine what you might want to look at when you're studying this data. But this is exactly how we do that. So this is one set of functions. There's a separate set for raster. So just keep that in mind. We'll look at those later. But these are all spatial relationships. Now, the one that is most common before we actually run these is called ST intersects. So that is, do two things intersect properly? Do they touch in any way? Do two geographic features touch, or do they cross? It will answer both those questions. But you can also answer, do they not touch, which is ST disjoint. You can ask if they cross each other. You can see if they completely contain, right? ST contains or within. Contains and within are basically the opposite of each other. So if A fully contains B, or within is A fully contained by B, which is just backwards. So those, just keep that in mind. You can see if they touch, only touch, not overlap, or you can see if they overlap. So or you can see if it completely covers or if it's covered by. So there's like these two types of things. True if A covers B, which is true if A is covered by B. So there's all these specifics within the predicates. But like intersects is like the one that's like, do they interact in any way? That's what I want to know. That's kind of your basic one. But I use contains and within as well, so you can keep those in mind here. But we're going to pull two things here. We're going to pull the data set of homes, which is our points, and our neighborhoods here. So we're just going to quickly look at that. Here's our polygon of homes, or sorry, neighborhoods here. And then what I want to do is basically run this SQL statement here. So this is going to look at basically for each home, is it in Ballard, right? ST contains in Ballard. And if you look at this, the function signature here will return which will return true if A fully contains B. So if A, the neighborhood geometry, fully contains the home geometry, it will return true if that's the case from homes, and we're going to join it on that same predicate. So this is a way you can actually join those data sets together. You could use a where here if you so choose, but I don't recommend that. I recommend using the join condition on, because this will equate to true or false. So we'll run a little bit faster. So it'll basically tell me, hey, I only care about the things that intersect with that, right? And then where, in my where clause here, is where the neighborhood name is Ballard. So if I did this right, all should return true, right? If I didn't have this condition, right, if I got rid of this here, joined on a different condition, it would return true or false depending on if it falls within that neighborhood. So just to illustrate kind of what's happening under the hood here, it's equating to true or false, right? All these will basically equate to that. Another one that we can do here is basically say, select the home sale ID from homes, join neighborhoods on, and this is a distance within, right? So this is kind of a separate relationship. As you see here, this is probably the only one that requires like an extra argument, but it's saying, is it within a certain distance of this separate feature? Right now, you might think, and this is a big mistake I see people make all the time, is they, okay, well, if I want to see if it's within something, I should turn that thing into a buffer and then intersect the buffer. But you have two operations there that are pretty heavy, right? The join and the creation. This just handles all of that in one nice little function that you have here. So if it's saying this is just creating the geometries, the transformation, and if it's within 500 meters of Ballard, so I can see there, I can see all the ones that fall within there, and you can see that there are 6,749 homes that fall within 500 meters or within the neighborhood of Ballard. So there are 500 that fall within 500 meters of it. Now you can see here's ST contains. This is kind of more looking under the hood. I'm not going to show you kind of all the things with the data here, but you can see that this one contains that one. I created this box from 0 to 10 to 10 to 10 and 0. So there's a box around that, and this 0.55 should fall right in the middle of that, which contains true. And you can see here that this one is right on the edge, right? So this is the same as this point. It does not contain it, right? It is not fully inside of it. If I switch this from 1 to 0, it's also right on the edge. So it's just the 1 and 1 that will go to true. So just to like show these things in action, that's how contains works. If I switch this to within, it might look different because the order matters with those. Now ST intersects for this, if I'm having, this is this kind of polygon 0, 10 again, and this is a line string that should cross it, right? I can show that here, and this does intersect that. And again, here, this is our case for a point, and since it's right on the edge, that is true, right? Now, ST touches, this is one that's also going to be touching on the polygon, and you can see that that equates to true. This one does not touch it, it actually falls within it, since it's 5, 5. That equates to false. So you just have to know which predicate to use. That's kind of my very kind of deep lesson on these is two things to take away from the section if you're using this data is, first of all, you need to know the order of the things that you're going in, and you need to know the relationship you want to understand. That's one. So you can use the documentation to see that in great detail. And then this is probably going to be the way you're going to be doing a lot of these spatial joins is right here, where you're going to join it on the predicate condition, right? And that actually helps filter out a ton of data that you don't need to look at, right? It's kind of like, you know, if you're doing a join in normal SQL and you need to like, hey, I don't need to pay attention to these IDs, and it cuts the data set down to 20%, that's a big efficiency gain. So using the join with that true false condition will be a good way to do that. So that's kind of my two takeaways using this, knowing your predicate, and that will be a big help for you going forward. So another common use case for Apache Sedona is to write geospatial data out in a variety of different formats. So there's a number of different formats that you can actually write data to. Most common of which is either a raster file or a partitioned GeoParquet file. And that's to process a large amount of data, push those files out, and then you can use them in that way. So let's take a look at the different writer options and we can explore how to do that. So we'll take a look at the raster writer first, and there's a few different ways to do that. You can write a raster data frame back to a binary data frame, which is basically using the arc grid and I think there's another one, ASCI grid. Those are the two. You can also write it out as a GeoTIFF, so you can convert it there. You use SQL as well, so you can do that way. And then you can also do PNG and a few different other options. So you can do all of that, and then you can basically structure it like this here. So you have a data frame, you create that raster binary as using that expression RS as GeoTIFF, write it to file, and then you can have all of these different kind of options and modes and formats. And generally it will partition the file based on the number of partitions you have in the data frame, right? So it will split it up, right? That's basically what partition means, to split up. If you want to write it as one, we'll show you some options to do that. And then you can do some other things here. You can write geometries as rasters, so on and so forth. So there's different options here. So GeoParquet is probably the most common data that's written out of Apache Sedona. It's an analytic format. And if you're familiar with Parquet data, it's just Parquet with a geography column. There's a few other things. You have some different versioning options. You can add in the projection. So you can see all those different things here. There's covering metadata to bounding boxes into row groups and stuff like that. And then there's all the other stuff you can do, which is you can control for the row group sizing. You can add compression. There's all these different things that you can do with that. So that's what you can do here. You can also write out to GeoJSON, and there are options here to do that. It will also partition the GeoJSON as well. And then you can see you can write out to shape files. And of course, you can write out to CSV as well. GeoPackage and shapefiles don't support writing, and there's some information on why that is. There's a collection of files that you actually have to write for a shapefile, and there's a 2 GB, size limit. So there's limitations on how large those can be. So usually you end up writing, I would say, either to a raster type or to GeoParquet, sometimes GeoJSON, but we'll show you how to write to GeoJSON if you do need to do that. So this is what this would look like. You can give it an output path. What we're going to do is we're going to coalesce this, kind of bring it into one single kind of, partition here and write it into one. So then you have the write, you have mode, overwrite, format, GeoJSON, and you save it to that path. So this will basically save it to a path here. We can take a look at that, and it should save it right there. So that it'll save it into that folder, and then it will actually add these different parts here. So this is the actual GeoJSON. As you can see here, here's the actual file. And then there's all these kind of metadata files that go along with that. And then this is basically the folder, right? So it saves it into an output folder. You can also do like if I wanted to write and partition the file to do write 10 files for parallel writes here, I can do that with the housing data frames. That's that data set that has all of the individual home sales. Once again, overwrite, format, and then you see here saving it to a specific folder. So that's what that will do. That will create the folder, which we should see popping up here shortly, and that should be in data. Here's the output, and you see here's the 10 different parts of that file. So there's the 10 different parts of that file there, and that's what that does. So you can write that out pretty efficiently. I'm going to get rid of these files since I don't actually need them around. And then you can see here that if you wanted to repartition this by a specific column, like the city it's in, it will do that. So one more there, we'll just show what that looks like. Here's the output of the partitioned. You can kind of watch the files be generated. And then here you can see that these are the individual cities, and there's parts that are within those as well. You can control, and I'm not going to get into all the weeds of how you partition and size and, kind of handle all the different stuff for, writing Parquet files, which there's lots of different documentation on. I'll try to link a video here if I can find a good one. But there's lots of ways to write out data there. And you can also, if you set up and configure this to write to a cloud bucket, this is just an example, right? You can actually write this directly to your cloud storage if you have the right, permissions, roles, all this stuff that you need from AWS from a keys, and you set that up all the way back at the top. You can actually write data directly to your cloud storage, which is really efficient. So I can prep data here, ship it into cloud storage, and let it live there. So there's another efficiency gain that you can do from there. But it's pretty simple. It's just adding more modes, formats, options, calls into the writing process, and then you can efficiently write out to GeoParquet, GeoJSON should you need the data for the web, or raster files from there. There's a bunch of other special stuff within Sedona. The one we're going to look at specifically here is the nearest neighbor join. I'm going to talk about that one. I'll talk about also some spatial statistics functions. So we'll take a look at both of those and show you how to leverage those, but go directly through the nearest neighbor join, since I think that's probably one of the more unique ones that lives inside of Sedona. This is the nearest neighbor join, or K nearest neighbor. And there's a number of ways to do this type of process in GeoPandas. You could do the same thing in PostGIS. You could do it in DuckDB, but this is the easiest way that I've seen to do that. And so there's a kind of a tutorial here that walks you through that. And this is the actual function call. So there's a specific function for a KNN, K nearest neighbor join, right? And you can kind of see what that looks like here, where you are basically passing in, there's a right table, left table, the K, or the number of things you want to find, and then the spheroid, which is basically finding the number of things, or the K number of things within nearest distance, right? So if you want to say find the 5 nearest things with a max distance of a certain distance, 5 miles, that's what you can do here. So that's effectively what you can do. So you can see here is you can create this view, select star from your Canon SQL, go here as KNN view, and then we can actually see an example of what that looks like. This is the query here, and you can kind of see what this says. You have a table of addresses and coffee shops. You'd like to find the 2 nearest coffee shops to each address. So here's table 1, here's table 2. You have the address ID, the coffee shop ID, and then your addresses, join from coffee shops, and then you just basically do that join, just like we did with ST intersects on STKNN, addresses geometry, coffee shops geometry, and 2, right? I think this kind of shows you what this looks like. This is transit stations within a certain distance here, so you can see there, and then I think you can also specify within a certain unit distance, right? So you can do, that's actually for STD within, but this is the STKNN. And then as you can see here, here's our point 1, here's the 2 nearest, here's point 2, here's the 2 nearest, and for this one, these are the 2 nearest. So it's a pretty simple process. You'll end up with basically 2 listings, or K listings, based on the number you put in for each one. This is A1, A1, A2, A2, A3, A3, and then it'll just kind of repeat like that sort of a list. So it's really efficient. This is the simplest way I've seen to do this. So it's really actually go ahead and do this. So yeah, that's basically it. If you wanted to add in like a distance constraint, like if you wanted the nearest 3, but only within a certain distance, like 5 miles, you could use a where clause of STD within. So you can see how you can start to stack these functions a little bit and start to combine them. But we're just going to look at a very simple KNN join here and take a look at what that looks like. So I'm going to repartition my schools data frame and then create a temporary view called schools of that. Okay, so what we're going to do here to do our KNN join is basically try to find the 3 nearest bike routes to each of the schools. So that's what we'll look to find. They may be different line segments or parts of that, but effectively we can still demonstrate the join. Both tables are in the 4326 projection, so that's why I'm going to use the true operator here to use the spheroid distance. So they're in the same projection. The distance, if I measure them, would be a little bit different. So I would need to transform them since it's in that decimal degree system. But for this, it should work just fine. So what we have here is a school name. So it'll be 3 repeating schools, and then the bike, the bike ID of the bike path. So it's just a unique identifier there. We'll join bikes on the STKNN, school geometry, bikes geometry 3, defining the 3 nearest, that's our K, and then true for the year spheroid. So that's what we'll do here. We'll go ahead and run that. And you can see here is that for this school, McGillivray, we have the ID of 6734, 1650, 24, and then so on and so forth. So you can see each of them have those nearest bike kind of like facilities or bike paths to them. So that's what you can see here. And you can obviously add in more stuff if you want to do, find specific, chunks of the bike paths. You could join them all to one geometry to find the actual bike path for each, or limit them by a certain distance. And you could do all those different things here to just add into this. But this is that basic structure. This is a pretty complicated join to do in other systems. So this makes it significantly easier, a lot less keystrokes, a lot less headache, and it's very, very fast. So that's one kind of unique piece I wanted to point out. I did want to point out some other different things here. So there's a few different kind of spatial statistical analysis I wanted to show. You can do some DB scan clustering here. So if you want to do more complex clustering, you can do that. There's also these specific like spatial statistical analyses, which one is GEDIS or GI star hotspot analysis. You can see that here, and it effectively does weights and hotspots around different areas. So that's another very common spatial statistical analysis to find kind of clustering, which will look at kind of the spatial density of these things and a number of different factors. So there are these like extra kind of spatial statistical pieces that I definitely recommend checking out. They might not work well on your local computer, so depending on the compute resourcing and the size of the data, you may want to look at some different systems there, but they certainly have a lot of scale and value to work with stuff like that. So DB scan, clustering, those types of things are available in here as well. So you can kind of check all those out. And then there's these other pieces like local outlier factor, so on and so forth. So there's a lot of stuff you can do just even beyond these basics, but the can and join is one that definitely deserves kind of like a highlight in my book. Okay, so next we're going to take a look at some raster functions. Now the raster functions I said exist separately from some of the vector functions, so let's pop over to the docs and take a look at that. So as you can see here, there are some different what are known as raster operators. There's a lot of different things that you might need to do with raster data, from data transformations to do geotransforms, figuring out the height of the raster, skewing, scaling. You can figure out the accessing different band values, and then doing some predicates like RS intersects, where these things intersect a geometry or contains, just like we had with the spatial predicates before. There's some different ones to set values, to change and modify values, to union values together, to set projections. A lot of the same stuff, but you see it, all these functions start with RS rather than ST, so spatial type, and then these are the raster functions here. So then we've already seen some of these, like the tile explode. You can turn the band values into arrays to make them more tabular. There's a lot you can do here, right? There's a lot of these raster specific things, and I won't get into all of these, but there's a ton of stuff that you can do to actually access the data here and do some different things. Some different things you might want to do to turn raster data into vector. You could turn the pixel into a polygon or a centroid or a point and stuff like that. And then you can, kind of do some different interoperability type of stuff there. So we'll get into the map algebra in a little bit. So I have a separate section on that, but these are some of the raster operators. So we'll actually take a look at those in a very short form, but this is a great library for working with raster data. If this is kind of the area that you work in, there's a lot of functions to do that. If you don't work in this area and you just want to use the data, that's kind of what we'll focus in on today. So I'm going to create this sample area. This is basically a bounding box, and I'm just want to limit the scope of the query just so everything goes quickly, because this, you can scale this up, and you obviously saw this covers a large amount of area. That entire area is broken into 30-meter grids, so or in some of the cases with the land cover data, 10-meter grids. So it's very granular data. So just to make sure things work smoothly, at least for the course of this video, I just want to make sure we limit that. So that's why I have that sample area there. So I'm going to load in and create the raster data frame as this land cover, and then what I'm going to do is basically create centroids from each pixel. So RS pixels as centroids. I passed the column, instead of geometry, it's raster, right? If you remember before, we have that raster column, so we have raster there. And then 1 is the band. There's only one band. Sometimes there'd be multiple bands of data. Like you saw, we have near infrared, red, green, blue, all of those different bands from the Landsat data. In this case, it's process data. There's one band, so that's all I need to worry about. So this works just like a SQL query from land cover. And then I want only where RS intersects raster, and I'm going to have geom from text for my sample area here. So that's what we'll do. And we can look at the first 3 values there. And this will still be a longer running query since that sample area isn't, it's small, but not, it's not, tiny by any means. So this will take a little bit of time to process this data. Like I said, we're looking at 10-meter grids here, and so it's a large amount of data there. Okay, so to perform this analysis, I'm going to take a really small area. This is this sample area that you see here. This is basically this park called David Rogers Park in Seattle, just to make sure everything moves and runs nice and smoothly for the purpose of this video. So because if you remember that raster data set is super large, we need to actually do that tile exploding. So I'm going to set up my sample area, and then I'm going to do that tile exploding here, but I'm actually going to save that as the new data frame, right? So last time we just did a show to actually show what that data looked like, and we'll save it there. And then we'll create our temporary view here. And then from here, I'm going to run this query. So this is rs pixels pixel as centroids, which will take each pixel and then return that as a centroid, as a point geometry, right? Now the arguments you pass here are the raster, which is like our geometry, the geometry column we've been using and everything so far, and then 1, which is the first band. Now some images like the Landsat satellite image you saw before has multiple bands in it. So it actually can have like the near infrared. There are 3 of those bands. There's a red band, a green band, a blue band, and all these different bands. Since this is just the land cover data, it just has the 1 value, so we're using 1 there. But there's functions to see, and you can access which is the band and how many bands are there and stuff like that in Sedona as well. So we do that, and then we want to just only get that for those areas that intersect. So instead of ST intersects, you can see we're using RS intersects, raster, and then we're creating that geometry on the fly using geom from text. We're passing that in here, and then that's what we'll do. So we'll create that function here, and then we'll show the centroids here from there. And then you can actually see what that looks like. We should get 3 different rows back. And these do take longer, even though it's still a lot, kind of large data. We're dealing with 10-meter granularity here. So it's, larger data, but, it still will take a little bit of time to run. But here you can see what that looks like. And this is actually a structured, or an array of structures. So if we take a look at our documentation, pixel as centroids, you'll see it returns a list of the centroid point geometry, the pixel value for the X and Y coordinates for each pixel in the raster at the specified band. So that's what it returns. It returns that kind of structured data value, and that's what that looks like. So we're doing a similar thing here where we're actually going to get the value from the raster at this specific point. So from that point, once again, RS intersects, it's within that area. So we'll figure out what that looks like, and then we'll actually show that and actually track how long this takes to run. Now, in case you do run out of memory, and this may happen depending on your machine and things like that, this may shut down given the Spark cluster that you're running. It means basically get an error that says Java heap space or something like that. So that's just another thing to be aware of, in case you do run into that error at any point in time. So this would actually return the values. It didn't look like we actually intersected any values here, which is okay. So that's we can skip over that one. And then we'll move into this. So this is, again, we're creating those raster tiles here from our land cover data set. And then what we're going to do is do some statistical discovery on this. So this is that same tiled data set. We're going to look for the summary stats here. And what this will do is show us those summary statistics, which if we look at that function, this will return for that entire raster, the count, mean, standard deviation, min, and max, right? So we can get all of those values across the entirety of the raster. And for each tile, you can see here, it does that. This would be the count, sum, mean, standard deviation, count, sum. These are all pretty similar. And then the different values across that specific tile. Similarly, we can get some metadata here. We'll pull it in for just this one tile where X equals 0 and Y equals 0. So we'll pull that as well. And then we should get that specific value. So for this one, where we want to get the metadata, so we'll get some different information about that tile. So the SRID, the skew, grid width, all this underlying information. Now, if you're used to working with raster data, this is a common process in Rasterio, or even using like a desktop GIS system, you can get this type of data back. So that's what you can see here. You can see the different values for those tiles. And yeah, those are the summaries to the metadata statistics, I should say there. So that's something that you can do from that perspective. All right, now we want to take a look at what's known as raster map algebra, which is just a fancy way of saying we're doing math and some pretty basic math across each cells, and you could even do it across neighboring cells and stuff like that, but within the raster cell. So when I say cell, I mean pixel in this case. Basically, what we want to do is perform what's known as an NDVI analysis, and that studies the vegetation amount using different bands of raw satellite imagery. So that image we saw from the Sentinel-2 program earlier is what we're going to use. So we can actually take a look at what that process looks like over in the documentation. So as you can see here, it's called Normalized Difference Vegetation Index. And that's a simple way to study from space the amount of vegetation that exists there. And you can see the math here. This is the extent of the algebra that you need to know at least here, which is NIR minus the near infrared band minus the red band, and then the near infrared plus the red band, right? And that's all that it is. And then you divide those two calculations together to get the NDVI. Now we use this language called, I believe is what this is called. So this is the GIFL script here, which is basically the band 3, 0, stuff like that. We're going to take the two bands individually and then assemble them together. So our code will look the same, but it'll have different things because we're actually pulling two individual bands. So that's what we're going to do. And we're going to measure the NDVI across the Seattle area using that satellite imagery that we saw way at the beginning of the tutorial. So that's what we'll get going here. Okay, so what we'll do is we'll create two different raster data frames. The first is from this band 084. And so if we go to this link here, we can actually see the individual bands we took a look at earlier in the tutorial. And you can see here that there's what we need is the near infrared 1 band. So you could download that here, and you can download that one. So it's B08 is the band number, and then the red, which is B04, right? So those would be the two band numbers. And you can download both these files here. I've included them in the data. So you can see B04 is our red band. So we'll create our data frame for the red band here. Just read the format, load, and then with column raster from GeoTIFF, which is what we have here. And then this is the near infrared band. And then we'll create temporary views from each of those. And what we do is we use this function RSUnion, which will basically take the two bands and put them into one single raster, right? So RSUnion will return a 2-band raster from these two data sets. And since they're exactly matching, because we use what's known as a stack or spatiotemporal asset catalog, we know it's the same time, it's the same exact shape, all of those things. You might have rasters with different shapes, which require some extra stuff to do, like clipping them to the same shape and ensuring the bands overlap correct, or the pixels overlap correctly. So there's all these kind of processing things that you might have to do if you were doing this. But if you're using this data, the same data set, stuff like that, it's pretty repeatable. So we'll do that here to pull those in. And then we'll create a temporary view from Union. And then we'll just run our calculation here. So we have our raster. Let's take a look at the docs and we can take a look at what each of these things is here. So we are using this function map algebra, which we can go to our raster operators and we can go to map algebra, which is right here. And you can see that there's some different letters that we could put in with this script. So some different types that you can add here that require the GIFL language and stuff like that. This is basically the data type that will get out. So it's a double. In this case, you can specify if you want that to be float or integer or something like that, but we'll just pass that in as the double data type here. And that's effectively all that we're doing there. So we'll run our map algebra. This is our script here. So it's the first, the second band 1 off of a 0 index. So this is the order. We have red first, then near infrared. So we have near infrared minus red, then near infrared plus red. That's our out script, and then that'll turn into our NDVI. So we can go ahead and calculate that, and let's take a look and see what that returns here. That returned the raster. As you can see here, we have that grid coverage, and then we can actually just visualize that. And so we'll pull that in. We'll use that same raster visualization script and return an image, and we'll see what the NDVI index looks like. All right, so this is the image that we created. And you can see where it's a lighter area, we're going to have a higher NDVI for vegetation, and where it's darker, it's lower. So here is like central Seattle. It almost washes out right into the ocean, as you can see here. And you can start to pick out where there's this built up environment. Anything that's lighter is going to have a higher NDVI, which means there's more vegetation there. So as you get out here, if you remember, this is a lot of cropland in this area and stuff like that. And then right down here, it's blank as well. And that's basically because that's the snow on top of Mount Rainier. So you have no vegetation showing visibly there. And then you can see the actual vegetation in these different areas. So that's what we got out of this. That was all the calculation we did. And then we can actually see these built up vegetation. And what's great about this is you can measure this over time. time. You can get a really good indication of, the vegetation and things like that and what's happening. There's lots of different applications for this I'm not going to go into in this video, but let's take this forward and actually do some stuff with this data in the next section. So I know I mentioned the raster writer before. I'm not going to run this locally because it requires a little bit more computing power than I have, established for my local machine. This is where something hoisting this in the cloud would be efficient, but you can see here that we can actually do that. If we wanted to actually export this as NDVI, this would be the code that we use. So I have that raster binary. I basically turn this into the GeoTIFF using the RS as GeoTIFF for this NDVI file. Can write that as a format raster, give it the raster field option, give it the path field. Here's the file extension, overwrite, and save. So that's what I would want to do there if I did want to save this. But I would recommend actually doing that within a cloud environment so you have extra computing power, because this is, it doesn't seem big, but this is large. And if you wanted to, you could scale this to a global kind of image creation if you wanted to go from there. So the other one I want to highlight is zonal statistics, right? Now, zonal statistics will allow us to say, given a polygon, whatever that might be, give me some statistics about the underlying raster data in that area. That could be the min, max, standard deviation. That could be the average, mean, anything like that. So that's what zonal statistics does. Let's take a look at those function calls and then come back here to actually perform this analysis. So what you can see here is that we have these zonal statistics functions. This is the signature here. So you have a raster or geometry, the band, integer representing the band that you want to pass in, and then one of the summary statistics. So you could have sum, mean, average, av, median, mode, standard deviation, variance, min, max, count, and the pixels. And you can do that there. Think of this as a combination spatial join, right? Where you're doing like an ST intersects, but on top of that, you're doing a group by, and then you give a statistical function on top of that. You can do that with a regular spatial join, point and polygons, count the number of points, give me the average of the values, the points, stuff like that. This is doing it with raster data. So in this case, what we want to do is actually do that for the NDVI data. So what we'll do is we'll basically create a temporary view from our NDVI data. We're going to pass in this park polygon. So what that looks like is this is a small park here in Seattle. So that's this area called David Rogers Park. And we want to find the NDVI for this little tiny area. What we'll do is we'll give it the zonal stats. Here's the NDVI. Now this would normally be called raster. Now this would normally be called raster as a column, but in this case it's called NDVI, which is the way we set it up. And then we'll do an ST transform to create the geometry. So we'll have in our geometry, which is just a raw WKT. We'll turn that into, instead of 4326, we'll turn that into a meter-based projection. And then we'll set these values here. So there's one for the band, which is one for the average NDVI across the entirety of the park. And then there's these false values here that I can set. These are optional parameters, but what you see here is if you wanted to all have them all touched, that's some different options you could set. If they want to ensure that everything is touching, excluding no data, which we shouldn't have no data because we created that value, and if there's leniency in terms of the touching. So those are all of the different pieces that you can have here. So you can see here's the operator for all touch. When true, any pixel touched by the geometry will be included. So that's kind of that like within or overlaps kind of or intersects use case. And then it's false, only the ones that are intersecting in geometry are included. So there's these little options that you can add in. Okay, so let's go ahead and set up our SQL. We'll repartition our data, and then we'll go ahead and show that here. So as you can see here, the NDVI value is 0.7, which is quite high, one being the highest. That makes sense. It's a park. There's a lot of green space. So of course there isn't all green space. If we take a look at this park, we can see that there's some other stuff here as well. And there's some, soccer fields that may be, fake grass or something like that. There are some tennis courts, and then there's some paths, and then the grass may be in full bloom during this time. It might be dead and brownish. So that gives us the indication that it's not all completely green, but there's a lot of trees, which you can see here, and that's probably where we're getting a lot of that full green space exposure from. So that's your NDVI calculation. This is pretty simple, kind of math, but then you can do these zonal statistics on top of that. And this really can scale up to do a lot of cool stuff. I'm gonna put a video up here that shows how you can do zonal stats with like 740 million buildings by hoisting that code into a cloud environment using Wherobots. And then you can actually scale that to do different things about flood risk and elevation and all of these other calculations. But there's a ton of value trapped away in like raster data. And it's not in like a normal analytics stack, but just allows you to bring that in and use it right alongside your other data as well. Okay, so one last thing I wanted to point out before we take this whole project and move it into the cloud in Wherobots is that you can actually move interoperably between two very common geospatial libraries. One is Rasterio, which is for raster data. And you can see here is that you can actually pull in a raster data frame just like this, basically collect all of those as rows and read that out as a raster and then do Rasterio-based operations there. I didn't build this code into the demo because for the rasters that we use is a little bit large. So you need a much smaller raster to do this unless you're doing this in a cloud environment, because it basically has to pull all that data in and pull that in as a raster file. So sometimes there's like some memory errors that tend to pop up. The other one is that you can actually work with GeoPandas interoperably, right? So you can move from a GeoPandas data frame and actually create a data frame in Sedona directly from that. So if I just read that in as a file, I can create a data frame. So if I already have some code in GeoPandas, it'd actually be quite easy to build this out and integrate that already into your Sedona workflow. It's in Python. It's just moving from the GeoPandas engine, which is in your memory in your computer, into the Sedona frame, the Sedona memory in Spark. And then finally, you can do a very similar thing here. You can actually, if you were to output this as a geo data frame and turn your Sedona data frame into a geo data frame, you can do that here. So there's this function on any data frame called toPandas in Spark. So you can see that here. And then what I need to do is I need to turn that as WKT and then basically add that as geometry. And then I can call GeoPandas, create the data frame from my pandas data frame and call the geometry from the WKT. And then you're directly into GeoPandas there. So if you feel more comfortable, if you want to do your data processing in Sedona, shift into GeoPandas, super easy to do. And you can actually do that here. So it's a pretty simple example. Just go to the docs and check this out and you should be ready to go from there. And our final step here, we're actually going to move this entire project into the cloud. Now, there's different ways to bring Sedona into the cloud, and we can actually check out the Sedona docs for that. So as you can see here, there's lots of different options beyond just your local setup. You can use this in Databricks. You can use this in AWS EMR, AWS Glue, Microsoft Fabric, Azure Synapse, and Spark Cluster manually. So there's all these different options here. Now, the easiest one overall is Wherobots. It's basically built to work with Sedona out of the box natively. So it's pretty much you just move your code and data in, and then you're ready to go from there. But if you do use any of these platforms, just be aware that you can actually access the instructions here and set that up in the different systems that you want to use if you choose to do it that way. But for this one, we'll be taking a look at Wherobots. And it's a cloud platform that is basically spatially optimized compute. And there's lots of other features that come along with this, which we won't get into today. I just want to show you how you take this project locally that you're developing and move it into the cloud and shift it up there. So if you don't have an account, you can go to wherobots.com, click try Wherobots and sign up here. There's a free community edition, which will get you access to everything you'll see here. So you can sign up and go through here. If you want to use the higher level runtimes, you can create an account with the AWS Marketplace, and that just works against your AWS account from there. So if you choose to do that, you can go through AWS and go through here. Otherwise, you can create the free community edition and go through there. So once you have that set up, you will log into your account and that will look like this. Now there's some different things here, but the first thing is that you actually need to get your data into Wherobots and basically into cloud storage. Now Wherobots comes with some free cloud storage as a part of the account through AWS S3, and you can do that here. So what you'll see is when you log in, you see this folder data. And then you see this customer ID that you see here. This is my customer ID. And the first thing I did was I created a new folder. So you can go here and create a new folder. I called it just like tutorial data, I think is what I called it. So if I can go here, tutorial_data. So this is my bucket now, and this is my S3 path. You can click the little clipboard here. You can say I already uploaded the data. So you could do that manually, but that's going to take a long time to do. So that's the way I wouldn't recommend doing that. What I'll show you how to do that is actually create a command line with the AWS command line interface and show you how to get set up with that. If you go to AWS, you can install the AWS CLI. There's instructions to do that here. Linux, there's also instructions on how to do that with, OS, Mac OS, and Windows if you want to do that here. So you can check out all these different options for installing that. You can get that set up here, but it's pretty easy to do. And there's different ways to do that. So you can Google that and check out the different ways to do that. You can ask ChatGPT or anything like that. But what we're going to do is basically lift all the files from that data folder that we had and pull that in. So I'm going to write my command. I'm going to write AWS. So you can see my command here is basically I'm telling it to do AWS S3, which is the service, and then sync I'm passing in the location of the data that I have. So you'll need to change wherever this is locally, but this is in that Sedona tutorial/data file where you download the data for the original part of the course. And then I gave it that path for that S3 bucket. So that's basically, I'm going to lift it into that folder. And then there's this argument recursive that will actually do that for me. So if I run this now, it won't be able to actually do anything. What I need to do is go back here, and on this upload, I click generate ingest credentials, which I'll do here. You'll actually get access to those. I'm not going to show you that step. I'm going to have to block that out since you don't get access to my keys. But if you hit that, you'll see there's this option for set environment and variables. You want to click that and copy that, and then basically run those in your terminal here. So what that looks like is I'm going to paste those credentials in. You won't see what those look like, but that's what I'll do here. And I'm going to just open up a new terminal window here on the side. And then I can actually just run those, and that will give me the authentication to load to that bucket. I run this command here. So if I load that up, it would actually run and start uploading files. I already did that, so I don't need to do that again, but you can run that and that'll actually lift all that data into S3 for you. So that's step one. You're just moving data from your local machine into the cloud as efficiently as possible, and you should be good to go from there. Now, once your data is all set up, what you want to do is actually start a notebook. That's on this main page here. If you're on the community edition, you'll have access to this tiny runtime. That's like the community edition. And if you don't, you can use some of these other ones as well for different scales of data. Basically allows you to scale up. And what you do is you just set that here. You don't need to change anything, but there's options to like have different Python environments set up if you want to do it that way. You can select the region you want to run in, and then you can get started. So once you hit run, it'll actually kick open the notebook for you. So I actually started one here, so then I can just open that up, and then you'll be open up to your notebook interface here. So that's what this will look like. If it's blank, it will look like this. And what you want to do is go to this home folder here, this very home folder, and then upload that notebook that you've been using. You can just drag and drop it into this area and it'll load up. And then we'll load that up here. Now you'll see first and foremost that the code looks different. So in our local notebook, we have all these options for configuring Spark, right? Wherobots handles that for us. So it's pretty much the same, right? We just have the Sedona context builder, getter, create, Sedona context builder, and then we skip all of these configuration steps. We just don't do that. And then we have Sedona context, create, config, right? Same as this line. So all the configuration stuff is done for you. You can add extra configurations if you want, but for our purposes today, you don't need to do a single thing. You're done from there. So you go ahead and run this cell. This will create the Sedona configuration. It may take a few minutes to connect, but once that's all set up, you should be good to go. So let's just zoom in. I'll show what that looks like. And then everything else should start working just fine, right? All those libraries that you need are already set up. So you can go ahead and run this. This will create the configuration to the compute environment that you're creating. That will set that up. And then from there, you'll be ready to go. So mine had timed out from the time I started it. So it turns off automatically. So you're not wasting compute resources. And then now I just have to restart that and go again. So starting that up again, and then I will be ready to go here once this is done. And that looks good. So now I have that, and you can see here that I'm creating my data frame, just all the same code we ran before, but this time it's all happening in the cloud. So this is nothing amazing here. This is just kind of our first simple examples. Let's go to the reading vector data section. Now, your data probably looks, or your code, I should say, looks like this, right? You have data / here. This doesn't exist, this data. So what I need to do is basically take this URL, or sorry, if I go here, zoom that out, storage URL, that path. So I can copy that to the clipboard again. And I just want to replace the data with that, right? So I don't need the 2 slashes there. And now it's going to run the same code, but from the data that's stored in S3, right? So that everything should work. So anytime you see where you have that data that's calling out to local data, you just need to replace that. But then all of your other code should work just fine. So if I have my geo package here, just replace that, read that there, and then I'm ready to go. So you can go through your notebook and just replace any of those instances, and then you're set and ready to run. So just to kind of show what this looks like, this is our NDVI analysis. I'm just going to go through and replace these and run those, show what this looks like. And you can see it's going to be pretty quick here to actually run that since I'm running in cloud compute. Overall, it's going to be pretty fast to actually calculate this. And then I can actually show all these different things here and write that. You can use some of the raster writers that I had kind of blocked out before since we were running locally, but everything's living in the cloud now and you're good to go. So we'll run that. And yeah, that's kind of as easy as it is to take an existing Sedona project and bring it into the cloud, especially with Wherobots where everything's kind of pre-configured for you and ready to go. If you're interested in taking this a little bit further, you can check this out. There's this, everyone comes with these examples files. These are some examples that myself and my teammates have made. So as this is running over here, there's lots of different examples for analyzing data. So you can go through here and check all of these different things out. There's different examples for, kind of reading and writing data, creating, map tile generation and things like that, connecting to different data sets. You can actually get access to that ESA world cover data that we've actually been using and use it at a much larger global scale. So there's a ton of stuff you can do here that takes it beyond that. And one thing that I'm going to do that I'm working on now is actually take some of this data and create a full machine learning pipeline to predict housing prices in Seattle using this data and some additional data. So if you're watching this video and I don't have a link somewhere around this video to that video, that means I haven't finished it yet. But if you're watching this at some point in the future and you see that link, you can actually take that further. We'll have a notebook and run all of that in the cloud since we need additional computing resources, but we'll actually create a full machine learning pipeline with spatial features to predict housing prices in Seattle. So make sure to check that out. But that wraps up this tutorial for Apache Sedona. That started locally and then lifting your project into the cloud. So thank you for watching along. If you have any questions, make sure to drop those in the comments. I will check those out. And make sure if you made it this far to head on over to get your certificate for completing the course. You can go through, take a quick test, get a certificate to kind of show and prove you've completed all the skills in Apache Sedona, running it locally and moving to the cloud. So thanks for joining along. Hope to see you in another tutorial in the future.